So I did the math of Pokemon. Basically, I just analyzed the equation for damage and tried to find a relationship between Pokemon and physics using math. So my purpose, find a correlation between mass and height versus stats of the Pokemon. Finding a correlation between force and damage versus force versus damage, and the base damage of the move versus acceleration, and then seeing what would happen if the 23 million damage attack occurred in real life. So I predicted two direct correlations, and then I was pretty optimistic with my hypothesis. I said the Paris would have enough momentum to move past the Earth's 6 feet velocity. That was completely wrong, but I'll explain it. So here's just a picture of the game. This also I figured out the length of the field. I figured that 0.2 was just a little bit of human error there, so I got 7 meters for length of the field. And I just used N64, Pokémon Stadium, and Lager Pro. So here's the damage equation. It's really hard to see, sorry about that, but
holy cow, it's really hard to see.
Yeah, I didn't think about that, but it's basically, since level was 100 on my trials, it's just, and modifier was always 1, 21 over 25 times attack over defense times base damage plus 2, and the attack of attacking Pokemon, defense of defending Pokemon, and then base was just the base damage of the move. And then I also used some physics equations. So here's my data tables. I basically graphed every relationship for like mass and height versus the stats. I left out special, which I would talk about, but I don't have enough time. And then, as you'll see, the only relationship I found is between the mass of the Pokemon and the attack plus defense, which you could kind of tell by looking at the equation, because attack and defense were the only two stats in there, and there's a correlation between force and damage. You'd expect mass and attack and defense to line up. And also I had 3 outliers on my graph, which I left out. Of course, it's a video game, so not every Pokemon would fit. And so 15% of my data didn't line up with the rest. And then whenever I got the graph, I just linearized it by growing the attack and defense. So here are my graphs. It's not the best correlation, but there is a bit of a correlation. And this is my initial graph. You can see there's a bit of like a parabolic relation. So then I just linearized it. So the equation told me 2 things. So first of all, I knew there was an amount of stats that every Pokemon would get normally, not dependent on their mass, and that was the y-intercept, which is 24,326, but you take the square root. And then the 102 is my slope, which was kind of confusing at first, but then I realized it was kind of similar to the average mass of all Pokemon. So then, or for just generation 1, because I only used generation 1 in my experiment, because it's a smaller sample size. So, and then using that information, I tried to create an equation to link mass and attack plus defense. So I got this Pokethagorean theorem. It's not an actual theorem. It's basically a squared plus b squared plus c equals d squared, where a is the mass of the Pokemon, b is the average mass of all Pokemon, c is a constant, and the d is attack plus defense. So, and it's not 100% accurate. In some cases, it doesn't line up that well, but here's some cases where it did line up pretty well. But mainly it's neat and it sounds cool. And then with part 2, I tried to find a relationship between the damage of the move versus the attack of the attacking Pokemon and defense of the defending Pokemon, because theoretically, if I divided the damage by attack plus defense, I would get acceleration, because force should equal, or damage should equal force, and attack plus defense correlates with mass, so force divided by mass would be acceleration. And also I had a typo in this graph. That should be 1.4 seconds. So here's the graph of damage squared versus attack over defense. Now this was expected, because basically the only thing that changed was the defense of the defending Pokemon. So as it had less defense, it would do more damage. That was pretty basic. But I noticed that the slope was 6,602, and that was within 0.3% of my calculated force of the move times the acceleration of the move. So what I did was, I don't know if this is hard to see, this might be hard to see as well, but I took the damage equation, squared it, divided it by attack over defense, and then I set that equal to force times acceleration, and then I solved for acceleration. And basically what this did was, it gave you a way to find the acceleration of a Pokemon move, knowing only attack, defense, mass, and the base move, for the base damage of the move. So it was like a link between force of the move versus the damage of the move, basically. And I tested it for one of my trials, and it was about 11% from my observed acceleration. So here's the 23 million damage attack. Now that's not actually possible in the game, but Pokemon is actually not actually possible, so I don't think it matters. I got, putting the stats into the equation for acceleration, I got 49.25 meters per second squared, which would be a force of 46,000 newtons, which is 10 times the amount of force it would take to break bone if delivered in a quick, sharp fashion, which is normally how Pokemon is. And I couldn't say for certain if the collision was elastic or inelastic, but it was probably more elastic, which would be 52.2 meters per second, which isn't even close to escape velocity, but if theoretically in Pokemon the energy could be created, which kind of makes sense in Pokemon, the maximum velocity of momentum to be conserved would be about 4.2 kilometers per second, which is closer. So basically, you can actually do video analysis on Pokemon, so nothing was like as exact as I would like it to be. And then I had 51% error between the slope of the graph versus the average mass of Pokemon, which could mean either just that my sample size had a higher mass than the average mass, which it did, or that there isn't a correlation, and just kind of coincidence that they lined up so well. But and then I say 3.6 there, but I did that with with a rounded version of my acceleration. When I actually did the exact acceleration, is only 0.3% error. And then 10% was, or 11% error was, my observed acceleration and my calculated acceleration using the equation I found. So, conclusion, just a mini approximation. So nothing in this lab was exact. It's possible that it was just a bunch of coincidence. It's because it's Pokemon. But I do think that there is a general link between math and stats that applies to about 80% of Pokemon. And damage or force are related and can be converted between each other. But only when modifier is 1. And modifier isn't 1 in case of like critical hits, super effectiveness, same type of attack bonus, stuff like that. That doesn't actually do with physics. And yeah, that's it.
Time for a question?
So the equation on like the first slide, did you like find that somewhere?
Yeah, it's programmed within Pokemon.
Okay.
So you say you use Logger Pro to analyze the image, but where do you get the image?
Oh, for like where I found the link to the field?
Yeah, from the game?
Oh yeah, I just took a screenshot of the game.
Yeah, but what about like other Pokemons? Because they're like Pokemon TV shows and movies.
Oh yeah, that's one of the things. I just had to assume that like most sources, like the handheld games, wouldn't be accurate because it's just trying to fill in the screen. So I just tried to find a game that would be the most accurate. And since Pokemon Stadium is on the console looking on the TV and has like the full range view of the field, it would be
Yeah.
the most accurate.
And actually, I do have an advice for you. Do you know Pokemon cards? Like, under the on the bottom of Pokemon cards, they have like the height and weight for all the Pokemon. So that would help, I think.
Yeah, I use a site called Bulbapedia, which is like a Pokemon Wikipedia to do height and weight.
Yeah.
Cool. Thanks again.
Like and subscribe.